This video is brought to you by Nebula. Watch episode 2 right now by signing up with the link in the description. Late on a spring evening, 1992, the Endeavour space shuttle, on its maiden flight, stood on its launch pad in Cape Canaveral, Florida. The crew sitting aboard, ready to take on a daring mission. A rendezvous between two spacecraft in orbit, a rescue mission. Bruce Melnick was aboard that day.
The challenge we had was that this satellite was never supposed to be touched by human hands once it got in orbit. It was supposed to be way up in geosynchronous orbit, over 22,000 miles up. But it launched on an unmanned rocket that failed to fire second stage and send it on its way. So it was stuck in a useless 800-mile high orbit.
Melnick and his crewmates were about to take the ride of their life to rescue the satellite, to grab it with their bare hands and attach a new second stage. But before that could happen, a complicated series of events was about to take place beneath them. 3 liquid fuel rocket engines were about to burst into life with furious power that would tilt the entire structure off axis, held back by just 8 explosive bolts, fed with turbopumps driving fuel out of the external fuel tank slung underneath the orbiter. Meanwhile, the 2 massive solid rocket boosters lay dormant, the 2 largest solid rockets ever made to date. And when the signal that the orbiter's engines were up to the challenge arrived, an inferno would be lit inside them, causing the entire column of solid rocket fuel inside to erupt, lifting the revolutionary, reusable space plane off the ground and to orbit. This is the insane engineering of the space shuttle. We are mere minutes away from launch. Helium and nitrogen have purged the main engines. The flight surfaces and main engine gimbals have been tested. The shuttle is now fully fueled and under its own power, no longer connected to the launch pad. 10 seconds are left. Sparkler-like igniters fire underneath the engine to burn any stray hydrogen as the shuttle prepares to open the main fuel valve. Liquid hydrogen begins to race through the fuel lines, pushed by the pressure of the tanks, through the engine nozzles where it begins to expand and turn into gas. This gaseous hydrogen drives a low-pressure turbopump turbine, elevating the rate of flow of hydrogen through the fuel lines. This is all happening in the blink of an eye. Less than a second later, the main oxidizer valves open, unlocking the fuel's true power. Fuel and oxygen meet in the 2 high-pressure turbopumps, raising flow rates even higher. Back in the nozzle, we see our first flames. Oxygen levels are still low, and combustion instabilities cause the engines to rattle. But the engine is now ready to enter its next stage, entering open-loop engine control, no longer controlled by a pre-scripted startup sequence. Instead, the engine constantly monitors pressure readings and adjusts valves accordingly. The engine begins to throttle up, oxygen valves continually opening wider. The flame transitions from a low-pressure orange flame to an eerie hot blue. The space shuttle is unique in that these engines are not directly under the fuel tanks. The expensive rocket engines were attached to the reusable shuttle, not the expendable external tank.
And because the main engines are offset from the solid rocket boosters, which are holding you to the pad, when we light off the main engines at 7 seconds, it actually bends that stack over, and you can feel this little lurching back and forth. NASA calls it twang, kind of a real technical term.
The only thing stopping the entire shuttle from tipping over at this point are the hold-down posts, attached to the solid rocket boosters, which for now lay dormant, waiting for the signal to ignite. The pressure inside the diverging nozzle is still lower than atmospheric pressure, and as a result, we can see a flow separation layer, which gradually creeps to the edge of the nozzle as the pressure inside increases. 3 seconds until launch. The engines are checked to ensure they are running at 90% of their rated thrust. The time has come for the solid rocket boosters to ignite. The solid rocket boosters are 45 meters long and are filled to the brim with solid rocket fuel, a rubbery mixture that combines both the fuel and oxidizer into one solid material. The oxidizer, ammonium perchlorate, makes up nearly 70% of the mixture, while 16% was the aluminium fuel. We need a way to ignite the entire column quickly. The igniter itself was essentially a miniature solid rocket motor, which itself was ignited by an even smaller miniature solid rocket motor. To ensure extremely quick combustion, this main igniter was shaped with a 40-point star orifice. When it comes to solid rocket motors, the more surface area available to burn, the quicker it will burn, rapidly producing the heat and pressure needed to ignite the entire column of solid propellant. Once this happened, there was no turning back, so there were several safety mechanisms in the arming sequence to prevent it happening accidentally. The first part of the arming sequence began when technicians accessed the safety and arming device in the top skirt of the solid rocket booster here to remove a pin. This pin locked a safety device in place, preventing it from rotating into an armed position by accident. When it was rotated into position on command at T-5 minutes, it connected a standard NASA detonator through a tunnel to the igniter system. When it fires, it begins the rapid chain of events that brings the space shuttle to its highest thrust. But the entire rocket is still anchored to the launch pad, held down by the hold-down posts, 4 on each solid rocket booster. These hold-down posts anchor the solid rockets to the ground through the aft skirt, with massive 711mm long and 88mm wide bolts. The lower side of the bolt is tensioned using a regular nut, while the upper nut is a special kind of explosive nut, a frangible nut. On 2 occasions, 2 of these frangible nuts did not fracture correctly, something NASA described as stud hang-ups. These issues did not stop the space shuttle from taking off. With the power of 2 solid rocket boosters and 3 main engines, 1 or 2 improperly fractured nuts were not going to stop the space shuttle from taking off. These hold-down posts were primarily designed to prevent the space shuttle from tipping over while the 3 main engines were brought up to full throttle, or simply by a gust of wind. However, if 4 or more of these stud hang-ups occurred, the issue could have been mission critical. And so, a redesign was introduced for STS-126, where a crossover assembly was included. This new system linked the 2 pyrotechnic charges in each nut to ensure they detonated within 50 microseconds of each other. A delay of up to 250 microseconds was possible with the previous design, and this was identified as the main issue causing the so-called stud hang-ups. The shuttle is now free, with the largest and most powerful solid rockets ever used in human spaceflight powering it upwards. Each of the solid rocket boosters provided 13,000 kilonewtons of thrust each, nearly double that of the Falcon 9 first stage. But the very notion of using solid rocket boosters for a crewed space shuttle was initially met with extreme concern. Using solid rocket boosters for human spaceflight had never been attempted before. They were nearly exclusively used for military use. Like the Minuteman ICBM, the solid rocket fuel allowed them to stand ready, available to launch in a moment's notice. However, once ignited, there is little that can be done to stop them. The entire column of propellant is ignited at once. There are no pumps or valves that can lower the fuel and oxidizer being delivered. Once ignited, they stay ignited until all of the propellant is expended. This, of course, comes with extreme control issues that need to be engineered around. To begin, the engine needs to be throttled back as it expends fuel. As fuel is used, the weight of the rocket lowers. If the thrust isn't lowered, the rocket could exceed its max allowable dynamic pressure and disintegrate. An improperly designed fuel column could make matters even worse, as a simple circular internal cavity will result in an increase in thrust as the fuel is burned. However, many different thrust profiles can be achieved with different shapes. A pointed star cavity will start with higher thrust thanks to the increased surface area, but rapidly decreases in thrust as the points of the star burn down and the surface area decreases. This effect can be increased by increasing the number of points on the star, which is why the igniter had 40. Nearly every illustration online shows the space shuttle solid rocket boosters with a continuous cylinder. If this was the design of the fuel channel, it could have caused issues. The surface area of a circular internal cavity would have increased as fuel was burned, because the cavity's diameter and circumference would be increasing. This was not how the solid rocket boosters were designed. The upper section of the solid rocket booster had an 11-pointed star shape. This shape was created with this mandrel placed inside the upper section before the fuel mixture was poured in. This shape then transitioned into a circular section. However, it wasn't constant in diameter. The diameter increased towards the nozzle. This design provided elevated thrust at ignition when it was needed most, and then reduced gradually to lower the maximum dynamic pressure the space shuttle experienced, with the thrust decreasing by 33% 50 seconds into the flight. When filling the solid rocket booster segments with the propellant, they were filled in pairs, matching with its contemporary segment on the other booster. This allowed the two segments to be filled using the same batch of fuel mixture. So, if there were any inconsistencies in the mix, they would be at the very least consistent on the left and right side of the shuttle, ensuring differential thrust from the boosters would not drive it off course. However, all 5 of the nozzles were capable of thrust vectoring to control the space shuttle during ascent, and 80% of the steering power came from the solid rocket boosters, thanks to their power and increased distance from the central axis of the space shuttle. The space shuttle's aerodynamic flight surfaces played no part in control during ascent, but they did actuate to reduce aerodynamic stress and drag on ascent. 7 seconds after takeoff, with the space shuttle traveling around 140 kilometers per hour, a roll program is initiated through asymmetric thrust vectoring of the nozzles of the solid rocket boosters with actuators mounted inside the aft skirt, here. There are 2 hydraulic actuators on each nozzle to allow it to move in both pitch and yaw. The space shuttle turns over 180 degrees and pitches 12 degrees off a straight-up trajectory, placing the shuttle on a heading towards its assigned orbit, lowering the dynamic pressure on the shuttle's wings and providing the flight crew a view of the horizon out of their windows. Of course, this 180-degree rotation would not have been needed if the space shuttle was simply rotated on the launch pad. But the launch pad was designed for the Saturn V. The position of the service tower and all of the supporting infrastructure associated with it locked the space shuttle into this orientation, and it was simply easier to program a roll than to build a new launch pad. 45 seconds into the flight, something fascinating happens. The space shuttle exceeds the speed of sound, and the sound of those rocket engines can no longer reach the astronauts.
So you don't hear those rocket motors that much anymore behind you. But now you hear the air rushing down the side of the shuttle because you're in the thickest part of the atmosphere, and it sounds like a train howling through a tunnel when that air is going across the rough blankets and tiles on the outside of the shuttle.
And as the space shuttle races higher and higher into the atmosphere and the air gets progressively thinner, even this sound begins to dwindle away.
For the last 15-20 seconds of first stage, it's just a quiet, very rough ride because you're still on the solid rocket boosters.
And it will get even quieter as the solid rocket boosters reach the end of their fuel supply 2 minutes into the flight. Lowering chamber pressures triggers sensors to begin the separation process. However, if these fail, a backup system based simply on time elapsed takes over. Once triggered, the thrust vectoring system is commanded to return the nozzles to the neutral position, and the orbiter is commanded to maintain its attitude for 4 seconds. The SRBs are attached to the external tank at 4 points, through 3 struts on the lower section of the rocket and an additional upper connection, each held in place by frangible connections that are severed on command. At the same time, 8 separation motors, 4 on the top of the solid rocket booster and 4 on the bottom, fire. These were also solid motors and provided 96,000 newtons of thrust, ensuring the SRBs safely detached from the space shuttle as it continued its flight to orbit. This solid rocket booster separation process was the thing that caught Bruce off guard most on his first flight.
Picture this, you're sitting on top of the explosive bolts that are holding the boosters to the tank. So when those explosive bolts let go, it's a large bang, and then the booster separation motors, which are little rocket motors that fly the boosters away from the shuttle so it doesn't recontact it, those exhausts are aimed right at your windshield. So It's staging, instead of there being this little pop and off you go in second stage, it's this big bang, and then you're in this fireball where the exhaust from the booster set motors are over the windshield, and it's like, geez, did we just blow up? And then very quickly, you get through that, and you can see the nice dark purpleness of space ahead of you. So that's really the only surprise going uphill that I had on my first flight.
At this point, the SRBs are continuing to climb in altitude, just slower than the space shuttle. Upon reaching their apogee, roughly a minute later, they will begin their journey back down to Earth, eventually releasing a series of parachutes from its nose cone to slow its descent and land in the ocean to be recovered and reused. Meanwhile, the orbiter is continuing its journey in its second stage of flight.
Second stage is smooth. Matter of fact, most astronauts will call it electric drive. But now's when the G's start to build up, and you're getting pushed further and further back in your seat. And then we throttle the engines back when we reach 3 Gs because it is a winged vehicle, so there's a lot of aerodynamics going on there. And for the structural integrity, we go ahead and throttle back to 3 Gs because the wings could come off if you accelerated a whole lot more than that, and that would make for a bad day.
Under the power of the 3 main engines, fed with the liquid hydrogen and liquid oxygen from the external tank, the shuttle continues its way to orbit. This external tank is a bit of an anomaly. The space shuttle was intended to be fully reusable when it was first conceived, with the fuel and oxidizer tanks incorporated into the orbiter itself. In fact, the space shuttle was envisioned in many forms. Ultimately, funding challenges forced the space shuttle's ambitious designs to be simplified, and the Air Force was approached to bolster funds, influencing the design to stray even further from the original vision, primarily in an increased cargo bay capacity and increased glide range. The external tank was, however, the largest compromise of design. Gone was the idea of a manned external tank that would glide back to land. What would have saved money in the long run simply would have been too expensive to develop, relying instead on an expendable external tank, a massive non-reusable structure that would disintegrate during re-entry. The external tank was heavy. It wasn't simply 2 pressurized tanks. It was a structurally integral component, responsible for transmitting enormous loads. It was the centerpiece of the space shuttle system, the structural backbone, connecting to both the solid rocket boosters and the orbiter. In order to do this, the external tank had to be strong. It was 47 meters long and weighed 33.5 metric tons, empty. Its aluminium skin is reinforced with strengthening rings and stringers. This was essentially a massive thermos flask with a spaced double skin to insulate the cryogenic fuel inside. Finally, the entire structure was covered in a layer of orange insulation foam, which alone weighed 2.2 tons. The first 2 space shuttle missions featured a white external tank, coated in a fire-retardant latex, which was removed to save a 1/4 ton of weight. The liquid oxygen tank was located on top of the external tank. It's much smaller than the liquid hydrogen tank, thanks to oxygen's much higher density, and this is part of why the liquid oxygen tank was placed on top of the external tank, as it pushes the rocket's center of gravity higher, an important aspect of stability in flight. If a rocket is traveling straight up, drag and lift acts through the center of pressure. The location of the center of pressure is determined by the location of the aerodynamic surfaces and engines, but the rocket rotates around the center of gravity, which is determined by the placement of mass. Because of this, it makes sense to place weight higher on the rocket, as it moves the center of gravity above the center of pressure. Imagine a rocket flying with its orientation aligned with its direction of flight. When a gust of wind knocks it off balance, it introduces an angle of attack, which creates lift acting through the center of pressure, and the rocket rotates around the center of gravity, returning the rocket to its original position. If the center of gravity was below the center of pressure, the opposite would happen, and the rocket would be unstable. So, the dense liquid oxidizer was placed on top of the external tank. This came with the added benefit of allowing the intertank to be placed higher on the external tank, as the hydrogen tank is much larger. The intertank is a load-bearing structure between the 2 tanks. There is even a massive beam hidden within this intertank, resisting enormous compressive loads as the solid rocket motors attempt to push inwards. The lower support holding the solid rocket boosters takes all of the shear stress created by the upwards thrust of the booster, and so the upper support acts primarily in compression. The forward attachment point to the orbiter is also located on the lower portion of the intertank. Of course, all of this liquid oxidizer and fuel needed to get to the main shuttle engines on the orbiter. The liquid oxygen exits the tank here. This pipe is massive, 46 centimeters wide, big enough to crawl through. When the liquid oxygen begins to flow, it acts much like water, and with this rate of flow, a massive whirlpool could form. With the weight of all this fluid swirling and sloshing inside the tank, this could cause massive instability issues, or it could even expose the outlet and allow bubbles to enter the engine. So, anti-vortex and anti-sloshing baffles are placed on the bottom of this tank where the oxidizer exits. Liquid oxygen travels down this pipe into the interstage, where it exits and runs along the length of the outside of the liquid hydrogen tank until it meets the primary orbiter connection point. This connection point connects physically to the orbiter, but is also the primary connection for the liquid oxygen and liquid hydrogen. To the left and right of this truss connection are two umbilical plates, which mate directly to corresponding plates on the underside of the orbiter. The left plate provided a connection for liquid hydrogen, and the right plate provided a connection for liquid oxygen. Each also had gaseous lines that brought back gaseous hydrogen and oxygen from the main engine to their respective tanks. This was vital in order to maintain ullage pressure. Ullage is the volume of gas above a liquid storage tank, like the cryogenic liquid oxidizer and hydrogen tanks. The pressure of this volume has to be maintained as the liquid lowers. If the pressure is allowed to lower, the structural integrity of the tanks could be compromised. The gaseous hydrogen used to pressurize the tank was tapped off from the hydrogen fuel line after it went through the regenerative cooling loops of the nozzle here at the outlet of the turbine exhaust manifold of the low-pressure fuel pump. Liquid oxygen did not pass through this regenerative cooling system and thus needs to be converted into a gas to pressurize the tanks. It instead was tapped off here at the outlet of the main oxygen turbopump after passing through a heat exchanger around the turbine of this pump. Finally, there were electrical connections on each plate too, made up of smaller electrical wires that provided power to the external tank and solid rocket boosters, while also carrying vital telemetry data from each of the orbiter's computers. Finally, there was also the liquid hydrogen recirculation connection, which was only used during the liquid hydrogen engine cooldown sequence before launch, where the cryogenic fluid is circulated through the feed lines, valves and turbopumps to bring them down to temperature. If this didn't occur, bubbles could form. The time for main engine cutoff is quickly approaching. The process will be triggered by a predetermined velocity target, around 28,000 kilometers per hour. However, it can be triggered by fuel and oxidizer sensors detecting a low fluid level. There are 8 propellant depletion sensors. The 4 fuel depletion sensors are located on the bottom of the liquid hydrogen tank. However, the liquid oxygen sensors were located downstream of the feed line, inside the orbiter. There was also an extra 500 kilograms of liquid hydrogen loaded over the required 6:1 oxidizer fuel mixture ratio. Together, these ensured that in the event the main engine was cut off as a result of propellant depletion, that main engine cutoff occurred in a fuel-rich scenario, as oxidizer-rich engine shutdowns severely erode and damage the reusable engines. The time has now come for the main engines to shut down and for the external tank to separate. Frangible nuts once again explode to separate the two structures. The external tank begins to float away, leaving the umbilical plates underneath the shuttle exposed, and fixing that is the next challenge.
You've got to close those doors. That's one of the first things you do. And that's very, very critical, because if you don't close those doors, you can't re-enter, because you'll burn up during re-entry. And so that's one of the things that we've talked about, we've learned about, but nobody has ever really thought about, or no one has ever really come up with an easy solution. If you had to do an EVA to close those doors, how you'd ever do it. You'd have to do a spacewalk back to the back here somehow and maybe hold on to there's just no easy way to get underneath there to close those. But we talk about it, we come up with some ideas, but
never had to be done.
Never had to be done, and there was never a procedure set to do it.
Thankfully, these doors successfully closed on every single space shuttle mission. The external tank is now on its way back to Earth's atmosphere, helped along by a vent opening in the oxygen tank that causes the tank to tumble away from the orbiter. With the thrust of the main engines gone, the astronauts have instantly become weightless. A serene moment that filled Bruce with so much joy that he forgot his first job as a rookie astronaut.
Now, we always took a nice close-up picture of the external tank right after MECO, because if you'll remember, the external tank was the only part of the space shuttle that wasn't reused. You know, the boosters would fly back or splash down in the ocean, we'd tow them back in, refurbish them, the shuttle would come back, but the external tank, as soon as we got off the tank, it would start tumbling back to Earth and break up and burn up, re-entering the atmosphere and just splash down in little pieces. So we always wanted to take a nice big close-up picture of the tank right after we got off it to see if there was any abnormality with it that might be generic that we'd need to fix before the next shuttle took off. So my very first job as a rookie was to, as soon as we got to MECO, instantaneously 0G, was to get unstrapped out of my seat, float down to a locker by me, get the proper camera out, float up to the overhead window while Dick Richards, the commander on my first flight, was pitching Discovery over on its back so that we could take a picture of this tank as it's following away back to Earth. Well, I floated up to the overhead window and I'm looking outside and Dick says, "Hey, Bruce, you should be seeing it." And I said, "Yeah, Dick, I do. It's awesome. It's beautiful." He said, "Well, why aren't you taking any pictures?" I said, "Pictures of what?" "Oh, the tank." I was so blown away by seeing Earth for the first time from the space shuttle that I choked on my first job. And, you know, I was supposed to have this great big picture of the tank. Well, by the time I took a picture of the tank, it was like falling away from us, but it was just beautiful. It was just seeing the Earth for the first time from space is, you know, probably my most memorable experience.
If you don't already have Nebula, for a limited time, we are offering lifetime membership, a one-off, one-time payment to get lifelong access to the world's largest creator-owned streaming service. Or maybe you have Nebula already and would prefer to switch over to Lifetime to get away from reoccurring subscription payments, while helping us accelerate growth of our platform without taking on venture capital money. Or you could be a happy member already and want to gift Nebula to someone special in your life, and for that, we also just launched gifted lifetime subscriptions. Whatever way you decide to sign up, you will be rewarded with exclusive video series like Wendover Productions' Logistics of series, detailing the logistics of arm manufacturing, search and rescue, commercial fishing, and much more. Or our own series about the logistics of D-Day, and early access to real engineering videos without any ads, like episode 2 of the insane engineering of the Space Shuttle, which you can watch right now. Normal yearly membership is $30 a year, or you can get the discounted rate of just $250 a month with the link in the description.